Hello everyone, welcome back to the lecture series on fundamentals of generative AI and large language models. In today's session, we will be discussing about Style GAN, which is another variation of generative adversarial network or what we call as GANs. So, we will have a look into the contents for today's session, limitations of traditional GAN and what is the motivation for Style GAN. Then we will get introduced to a concept of latent space entanglement, then introduction to Style GAN, the mapping network, affine transformation, synthesis network, adaptive instance normalization, and then the style based generator as a whole. So, let us start with the limitations of traditional GAN and what is the motivation for Style GAN. Now, we all know in traditional GAN, we give a noise input to the generator, and the noise is basically a random vector which is sampled from a normal distribution with mean 0 and variance 1, and this noise is basically it's from the latent space which have a lot of information which is compressed or hidden inside, okay. And when this noise goes through the generator, we get an image, generated image, okay. So, in this case it is a image of a butterfly, okay. Now, GZ means it is a generator or the noise is going through the generator G and we are getting an image. Now, the limitation of these GANs is, suppose I want to change the color of the wing. Can I do that one independently without changing the pose or the posture of the butterfly? So, that is the limitation. It is not possible in traditional GANs. So, what is the motivation for Style GAN? Suppose I have an image of a lady and then I want to change the color of the hair of this human face to blonde, from brown to blonde. Now, is there a way I can map that any one of these latent variables, if I change, I can change the color of the hair from brown to blonde, but it is not there, okay. So, once again, if I want this human face, this is smiling face and this I want the smile to go off, okay. Can I have a fine control on the latent vector that I am putting inside the generator? Can I control which latent variable I can change so that the smile goes off and it becomes a different kind of a facial expression? That is not there, okay. And similarly, if I want to have specs, can I match it with one of the latent variables? Can I change that one and the specs will come? No, it is not there, it is not possible. So, in traditional GANs, this control over the style of the face, facial expressions or the finer details, it is not there. So, researchers wanted finer control over the generated image attributes, okay. Image attributes in this case, it can be the hair color, it can be the smile, it can be the glasses in the face, okay. So, those are the image attributes and this was not possible in traditional GANs. So, I have taken these images from a website called thispersondoesn'texist.com. So, that is entirely for explaining this concept. Now, I will come to a very important concept called as latent space entanglement. Now, what is this latent space entanglement? Suppose I have the image of a face of a human and once again I have the latent vector, and suppose I want to change, as I was telling, the color, the hair from brown to blonde. Now, think of if I am changing some of the latent variables, then what happens is, for changing the color, first of all that mapping itself is not there, that there is no specific mapping which latent variable which control which attributes. Just for example, I am telling that any latent variable, if I change that one, maybe it will change the color of the hair, but at the same time it will change the shape of the face also. Okay. So, it is not that independently I can change the color of the hair. Together with the hair color, the structure of the shape also is changing. Similarly, if I want here like the blonde color hair to change to black, I am saying that when this transition is happening, there are some freckles that are coming. So, it is very difficult to have control independently. So, what the meaning is here, what is the meaning of this latent space entanglement is one latent variable affects multiple image attributes simultaneously. So, if I take one of the latent variable, it may change the color of the, it may change the color of the hair from blonde to black, but at the same time there was no freckles, here some freckles have come. That means multiple attributes are entangled, and changing one latent dimension affects multiple semantic attributes. So, independently we are unable to change the attributes of the image. Okay. So, that concept is called as latent space entanglement. Now, what is the reason for this latent space entanglement? Why this is happening? For one particular latent variable, multiple attributes are associated. Why? It is told that the input latent space must follow the probability density of the training data, and that leads to unavoidable entanglements. So, it is kind of a a textbook kind of a statement which I have put here. Now, we will understand what exactly is the meaning of probability density of the training data which leads to unavoidable entanglement. So, we will try to see what exactly it means. So, here I have lot of pictures of human faces, some are from some are ladies, some are gents, and there is a mixture. So, this is my data set of human face. Now, if we see if we see the short hair is belonging to the most of the image data set. In this image data set, at least the short hair is belonging to the male face, whereas the long hairs are belonging to the female face, okay, the ladies. Now, this is my data set. It may have other things like short hair for ladies as well as long hair for gents people. Now, the thing is, if your model of, or if our model is trained on this data set particularly, where short hair is shown with the facial attributes of a male person and long hair is shown with facial attributes of a lady. So, then what happens is there is an entanglement that is happening with the facial attributes and the length of the hair. Okay. So, that means the multiple facial attributes, that means the hair as well as the features of the face, the eyes, the nose, the lips, those are becoming correlated. Okay. And what happens is the latent space becomes curved because the generator avoids producing unlikely combination. If my data set is having equal amount of ladies and gents who are having long hair, then this problem will not come. But in case our data sets are having short hair for gents people and long hair for ladies, then the generator is unlikely to make those kind of make unlikely combinations. Okay. So, that is the thing, and this is what we call as the latent space entanglement. That means with the size of the hair, the facial attributes also gets correlated. Okay. Now, the requirement or the motivation for getting independent control over the various attributes of human face was the main motivation for introduction to Style GAN. So, we will look into what is this Style GAN, how its architecture is different from traditional GAN. So, in traditional GAN we have latent vector Z which goes to the generator. So, you have the latent vector directly going to the generator for producing images, whereas in Style GAN you have the latent vector, then you pass it through a mapping network F, and this mapping network maps the Z latent space into an intermediate latent space W, and this latent space W is responsible for putting style in your image. Okay. So, the main difference is the latent vector Z, instead of directly going to the generator, in this case, in the case of Style GAN, it goes to a mapping network F and then it goes to the generator. So, in between the latent vector input and the generator there is a, so this is the input and this is the generator, in between there is the mapping network. Okay. And this mapping network, it maps the latent space Z into an intermediate latent space W. We will look into what is this mapping network looks like, what is its function as we go through the slides. So, this is for Style GAN, and this allows different image attributes to vary independently. That means, in this case in Style GANs, if I want to change the color of the hair, I can change it independently without changing the shape of the face. Or if I want the smile to be reduced, to be little bit reduced or increased in a facial expression, that can be done independently. Okay. Now, this concept of Style GAN was first introduced by Tero Karas and his team. They are scientists from NVIDIA on the paper, in the paper A Style Based Generator Architecture for Generative Adversarial Networks. Okay. So, once again a kind of a pipeline if we can frame in our mind. So, Z goes to the mapping network gives W, which is an intermediate latent space. This is responsible for giving you styles, different styles, and this goes to the synthesis network, which is basically your generator, and then an image is produced. So, this is the pipeline for Style GAN. Now, we will see the mapping network and the W space in Style GAN, what exactly it is. So, we have this latent vector Z. In case of Style GAN, it is Z is sampled from a normal distribution with mean 0 and variance 1. Typically, Z is having the dimension of 512. So, this belongs to a space of 512 dimensions, and this vector contains all the information in a compressed form for generating images. Okay. Now, this goes to the this goes to the mapping network F, and what is this mapping network consisting of? It consists of 8 layers of multilayer perceptrons. Okay. So, these are all fully connected layers, and what is the function of this mapping network? It basically transforms the entangled latent space Z to a more disentangled latent space. Okay. So, the entanglement that was there in the latent space Z, that becomes much more disentangled in latent space W. Okay. So, that is the function of the mapping network. So, once you are in the latent space W, you can change styles independently. That means one latent variable or one direction controls the pose, another direction controls hairstyle, another direction can control smile and eyeglasses. So, independent control is possible, and then this goes to the generator. Now, in traditional GANs, the generator directly begins the image creation from Z, we all know. So, it goes directly, it goes in traditional GAN, it goes from the Z goes to the generator and generator generates the images. In Style GAN, it is little different. So, what happens? First of all, Z goes to the mapping network. Secondly, the Style GAN, it starts the generation with a fixed learned tensor. What is this fixed learned tensor? It is a tensor of size 4 cross 4 cross 512, and 512 is coming because of the dimension of the latent space there, and this tensor is initialized with constant values, and during back propagation these values are updated. Okay. So, this is a learned tensor. Okay. So, the style GAN starts the image generation not from Z, but from a learned fixed tensor or fixed learned tensor. Okay. Now, we will have a look into the mapping network in style GAN, how it looks as I was telling. So, this is my latent space Z, it is normalized, and then it goes to 1, 2, 3, 4, 5, 6, 7, 8 layers of fully connected layers, and we get W here, and these are basically all these are multi-layer perceptrons, and the dimension is 512, and W, as I was telling, Z space becomes disentangled, and we get all untangled attributes. Okay. And then what happens here is, till this one we have discussed. Now, from W we have told that it goes to the generator. Now, before it goes to the generator, there is something called as the affine transformation. It is a mathematical operation that is done on this latent space W. So, what exactly happens here we will see, and after the affine transformation is done, it goes to the synthesis network where actually the image generation happens. Okay. So, we will look into what is this affine transformation and how the styles are getting incorporated in the generator network. We will see that one. Okay. Now, as I was telling, in traditional GANs we have the Z directly going to the generator and the image generation starts from there. But in style GAN it starts from a learned constant tensor. Now, what exactly I mean by that one? Suppose I have a sculpture artist, and this is day 1 where the artist have started with a clay block, this one, and then the final output that she has sculptured out is this horse. Okay. In day 2, the artist once again sit with the similar block, and she, the artist creates a horse which is having different style than the day 1's horse. Okay. Think of this situation. So, what we are seeing here, same starting clay block. So, both the days they have started with the same clay block. Day 1, the style of the horse, sculpture of the horse is different from the style that has come out in day 2. Okay. So, even though we are starting from the same clay block, the final outputs are different. Now, we can think of this one, this clay block or the starting point is the fixed constant or learned tensor. So, it is fixed, but the final output is different in style GAN. So, what is that part of the model which is bringing this difference in style? The style is injected through adaptive instance normalization, which we call as ADA-in, and then we have noise injection for making finer stochastic differences between images, and it is not from the initial input tensor. So, the input tensor is as a starting block, behaves as a starting point, and then different styles are incorporated in the different layers through this adaptive instance normalization, which we call as ADA-in, and noise injection. Okay. So, this is the analogy of style GAN. So, we can think of the learned constant tensor, which is 4 cross 4 cross 512, that is the starting clay block, and then in the process the styles will be injected, and ADA-in have a very significant role to be played in the style injection. There are affine transformations, then ADA-in, there are convolution layers, all these are a part of the style injection, and then we get an output image. Okay. Now, we will look into what is this affine transformation in Style GAN. Now, affine transformation, they produce the styles. When I tell affine transformation, what exactly I mean by the term affine transformation? Suppose I have an input x and it goes through a transformation y equal to wx plus b, where w is the trained weight matrix. So, this is called as an affine transformation. Okay. Now, in Style GAN what happens? We know the latent space now gets mapped to the latent space w, latent space z gets mapped to latent space w, and then w goes through an affine transformation and we get y equal to aw plus b, and this is again one matrix, and what we get, the y is basically the style parameters. So, after the affine transformation y equal to a w plus b, we get whatever y's are coming out from there, they are basically, these are basically style parameters. Okay. And these style parameters get injected layer and at every layer, adaptive instance normalization or ADA in block at every layer. Now, the affine transformation converts latent vector w into style parameter that we have already seen. Now, as I was telling that the 4 cross 4 cross 512, that is your starting clay. Styles are the sculpturing instructions that are put all throughout in the pipeline through the affine transformation and ADA in. So, the full architecture flow looks like this. It has two parts. Style GAN has two parts. One is the mapping part, one is the synthesis part. And we have seen mapping part goes from Z to W, and synthesis part, it takes care of the image generation, and this produces disentangled latent space distribution, and synthesis part is the part where exactly the image generation happens, and it starts from 4 cross 4 cross 512, and this tensor is trainable. So, it gets trained in the process. Now, how are this mapping path and the synthesis path, they are connected together, how that is happening? So, the connection actually happens through convolution layers. There are 18 convolution layers. So, what exactly is happening in these 18 convolution layers? So, we know this W is now going through affine transformation and giving us Y, and which are the style parameters, and at every convolution layer affine transformation produces a style parameter that are injected through ADA in. So, we will look into in the next slide, probably it will become more clear what exactly I want to tell. So, you have the fixed learned tensor which is 4 cross 4 cross 512, and this is the starting point, it is kept constant, and then it goes to convolution layers. This convolution layers, as I was telling, there are 18 convolution layers, and then these convolution layers goes through, it produces the feature maps, and then these feature maps goes through ADA in. Okay. Now, these feature maps, they contain the edges, textures, face structures, everything. So, I will talk about what is the function of ADA in a few minutes later. Till now, let us just have a look. This is the synthesis network. This is different from the mapping network, and the synthesis network starts its work from this fixed learned tensor, goes to the convolution layers. There are 18 convolution layers, and these convolution layers generates the feature maps which have the edges, textures, structure of the face and everything, hair pattern, everything. Now, what is the function of ADA in? I have told about it. I have told ADA in is a very important, plays a very important part in the style injection. What exactly it does? ADA in does two work. One is it normalizes the feature map. When it is normalizing a feature map, it is basically erasing out all the original statistics that is there in the feature map. Okay. So, it is just erasing the styles that are present, and then it is applying a new style using learned scales and biases. From where these learned scales and biases are coming? They are coming actually from the affine transformation. Okay. And as I was telling, the convolution layers, let us put our attention here now. I have told about what exactly is the function of ADA in here. We will look into more details of this one in the next slide. Right now let us concentrate on these convolution layers. Now there are 18 convolution layers, and after every 2 convolution layer there is an upsampling. That means the resolution improves. Okay. So let us have a look. Suppose we have convolution layer 1 and 2. Then if this is upsampling, this goes upsamples, and then 3 and 4, then 5 and 6, and if we see the resolutions, it starts from 4 cross 4, then after 2 convolution it goes to 8 cross 8, then 16 cross 16, and these are the low resolution part which learns the pose, the face shape, the coat structures, the shape, the edges, and the pose of the face, everything. And then again it gets upsampled convolution 7, 8, 9, 10, 11, 12. They are having the dimensions of 32 cross 32, 64 cross 64, 128 cross 128, and these middle layers learn the eyes, nose, hairstyles, everything. Okay. And then once again upsampling. So after every 2 convolution layers there is an upsampling. Again we get 13, 14 and 15, 16, 17, 18. So 13, 14 is 256 cross 256 resolution. Then we have 512 cross 512 for 15th and 16th convolution layer, and then this 17th and 18th are having 1024 cross 1024. So the resolution keeps improving, increasing with the number of convolution layers, and these higher resolution layers learn the pores, the wrinkles, the very finer details, the texture of the face. So these are the features that are learned in the high resolution layer. So we have these lower, mid and high resolution layers to learn not only the coarse features but the finer textures also. Okay. Then we are coming into the adaptive instance normalization, which we call as ADA-in. Now what is this one? So as I was telling, if you look into the previous slide, the feature map that is generated by the convolution neural net, the convolution layers, that goes into the ADA-in. So let my feature map look like this, and then ADA-in does, it normalizes the feature map. And what exactly in normalization we do, we take the mean and the standard deviation, and we do the normalization process. So if we take the mean here, so this mean is calculated like this, and standard deviation is calculated for this feature map. This is the standard deviation. If there are any mistakes or any calculation things, mistakes are there or typos are there in these calculations, please feel free to reach out to me, or you can just check if the calculations are correct or wrong, or you can change it by yourself also, because standard deviation and mean, these are very standardized formulas. So you can just look into it. Now when ADA-in is normalizing the feature map, it takes this normalization formula, xi minus the mean divided by sigma, okay, which is the standard deviation, and then we have 0 mean and unit variance feature map, and this is what I have done the calculations for you. You can just pause and have a look. After normalization, what happens? The old style informations are removed. That is the main reason for doing this normalization process. Only structural information will be present. So this is the normalized feature map, and over this one the styles will get injected. Okay. And ADA-in first normalizes every channel independently. So every channel that is coming in the feature map, this gets independently normalized by ADA-in. Now how the style injection in ADA-in happens? So we know that this is our latent space Z. Through the, when it goes through the mapping network, we come into the latent space W. The difference between Z and W is this is the entangled latent space, and W is disentangled latent space. And then it goes to the affine transformation, which produces the style parameters. So affine transformation y equal to AW plus B, and if we take the vector. So, we have two components ys and yb. These are used by ADA_in. Now, what is this ys and yb? These are the two components of y vector, and ys basically it is a sorry, this I will not come. Ys and yb, these are the learning scaling parameters, and yb is the learned bias parameters. So, there are two parameters, one is the scaling parameter and another one is the bias parameter, okay, and they come out after the affine transformation. Okay. Now, if I have these parameters ys and yb, what does ADA_in does? So, we have already normalized now, or this is the step of normalization, if we can say this is the normalization step of the feature map. Then we are multiplying this one with ys and y and adding this bias term yb, and this is done for your ith layer. Okay. So, this I gives it in which layer you are doing it. So, this is the ith layer, and every layer it will get changed. Okay. So, ADA_in normalizes this one, this is the normalization step, then it gets multiplied with the learned scaling parameter, and the learned bias parameter also is added here, and then we get, this is the way the style is injected into the ADA_in block. Okay. So, styled feature maps are generated which are coming out of the ADA_in block, and we get the generated images. Okay. Just for giving an example, if y is equal to 2 and yb equal to 1, I have just given a numerical example. So, it is 2x into whatever you have got in the previous normalized feature map plus 1 comes from yb, and you have this. This is basically your styled feature map, this one, this is your styled feature map. Okay. Now, so up to this we have understood how from the entangled latent space, how we are coming to a disentangled latent space using the mapping network. Then we are going through the affine transformation. What is the affine transformations work? It produces the style parameters. What are the style parameters? In this case, this is ys and yb. They are going as input to ADA_in block. And what is ADA_in block's work? ADA_in first normalizes the feature maps that are coming out of the convolution layers, and by doing this process it erases out all the statistical information that is present, only keeping the structure intact, and then style is injected through this ADA_in block through this style parameters. Okay. Now, we will have a whole look or look into the overall picture, how the style based generator looks like. So, this image I have taken from the original paper, and you can look into, you can go back to the paper. I urge all the participants to look into the paper, lot more details you will get in the paper. So, this is the traditional one where we have latent Z going into the fully connected layers and we get the image generation, whereas here this is the style based generator, and you see the latent entangled latent space, it goes through the mapping network. Mapping network is 8 layers of fully connected multi-layer perceptron. Then we get this W, which is the disentangled latent space. Then these W goes to the affine transformations A for all different layers it is going, and if you see, this is the synthesis network. As I was telling, it is starting from constant 4 cross 4 cross 512. Then this affine transformation is giving you some style parameters which is going into ADA_in, and again there are convolution layers, and then it is going through the process. And then the thing that I want you all to look into is there is something here, and there is some noise injection that is happening in these layers. Now, what exactly is this one? Noise injections are happening. Here is noise adds stochastic variation to the synthesis network. So, basically very finer details that will change, that will be different from one image to the other image, one generated image to the other generated image, because we do not want exactly the finer details we want a stochastic variation of that one, and that is the reason the noise gets injected. And what is B? B is a learned scaling factor. It decides how strongly the noise can affect each feature channel. So, this is how the entire process flow works in a style based generator or in Style GAN overall. So, with this one I come to the end of my session today. Before I conclude, let us have a quick revision or a summary of what we have learnt in today's discussion. So, we have seen that in GANs, any form of GANs, control on the finer details or attributes of any human face or any image was not possible with the traditional GANs. Just to have an independent control on the styles of a human face, the emotions that it depicts, or other attributes associated with the face, facial expressions, that was the motivation. Can we make attributes vary independently? That was the motivation for this Style GAN coming into existence, and scientists discovered this architecture. And what this architecture, the main difference is basically it takes the latent space, which is an entangled one, changes into a disentangled latent space, then it gives it to the generator, which generates the image. And for changing the latent vector from the latent space which is entangled to the latent space which is disentangled, there is a mapping network which is there. It takes care of the transition from entangled latent space to the disentangled latent space. And after that one, whatever is coming out from the mapping network, that goes through some affine transformation. These affine transformations basically give you some style parameters. So, these style parameters then gets injected at various layers of the synthesis network, and this synthesis network, which is different from the mapping network, this starts with a fixed learned tensor of shape 4 cross 4 cross 512, and then this is fixed and the styles get injected at every layer. And for style injection, after the affine transformation, whatever style parameters we are getting, that goes and gets injected into the ADA-in block, and then ADA-in takes care of injecting these styles into the images. What does ADA-in does? It first normalizes the feature map that is coming from the convolution layers. By normalizing, it is actually erasing all the styles that are present there, and then it is injecting, or it is taking the style parameters that are coming from the affine transformation and putting them there in that feature map. Okay, and that is the way the final image gets produced. Okay. So, that is the summary of the working of Style GAN. With this one, I conclude today's session. In my next session, we will be discussing about Style GAN 2, which is another variation of Style GAN. And till we meet for the next session, thank you all and happy learning.